All right, welcome everybody to today's webinar. We'll be talking about simulating conjugate heat transfer multiphysics with HELYX. Today's goals, I want to introduce ENGYS and some of our multiphysics innovations, learn the main features of meshing, setup, and solving within HELYX. And it would be great if you could obtain a sense of how conjugate heat transfer cases are easily set up, easily meshed and set up within HELYX. And just for the sake of time, we'll answer all the questions at the end and continue via email post-webinar if there's something that I didn't answer during the process. Just a little bit about ENGYS. ENGYS, we are global providers of CFD products and services. We were founded in the UK in 2009, so we're celebrating 10 years. We just finished our 10th year. And since we started, we've always been focused on enabling open source software in industry. We have extensive experience with OpenFOAM, and we've been developers in that library since 1999. So if you're familiar with OpenFOAM, you know that before its release in around 2005, it was a library called Foam. So we have people on staff at ENGYS who have been working with this code base from the very beginning. We have 7 offices worldwide in the UK, Germany, Italy, here in the US, Australia, South Africa, and Brazil. And we have an established network of distributors in Japan, South Korea, here in the US, France, and Spain. With respect to our products, we have 4 main groups of products. We have HELYX, which is a general purpose open source CFD software suite, and that's what I'll be talking about today. We have Elements, which is almost a superset of HELYX, and then it has more tools that are specifically directed towards the automotive industry to improve automotive design. Next, we have a group called HELYX add-ons, and within the add-ons, these are modules that deal with adjoint optimization, block-coupled solvers if you're working in turbomachinery or compressible flow, marine hydrodynamics, and also advanced multi-phase flow simulation. Finally, we have HELYX OS, which is an open source graphical user interface for standard OpenFOAM that is offered for free. And if you go to our website, www.engys.com, and you look for our products, you can find HELYX OS, and it gives some information about how to download that GUI. So today, I'd like to talk about several different topics. So for some people that may not be familiar with conjugate heat transfer, I'll start with what is conjugate heat transfer. Talk about the modeling approaches, talk about the solver within HELYX, provide some information about success stories, and then go over the enabling features of the GUI. Then I'll do a demo and I'll leave you with some take-home messages. So let's start off. What is conjugate heat transfer? Well, conjugate heat transfer is heat transfer that involves heat moving through multiple fluid and solid domains. And also, there's heat exchange at an interface between these domains. For example, electronics cooling, that's a great example because we've got circuit boards and we've got different components that are heating up, electric motors, heat exchangers. In the power generation industry, we're taking thermal energy, especially for doing combustion, and we're extracting that thermal energy and trying to generate electricity using that. Clutch simulations, there's lots of heat generation during the process of using an automotive clutch, driving around. And then another one would be heterogeneous catalytic processes. So if you've got a solid catalyst and you've got gases flowing in with different chemical species, they'll diffuse inside of these solids. They might be generating heat, so there's heat diffusion inside of these solids, and then also convection and all sorts of other physics within each one of these. So with these different systems, we need to capture the combined physics. So natural force convection, conduction, radiative heat transfer, generation and consumption terms, and then also contact resistance at the domain interfaces. So let's talk about the modeling approaches. For modeling a conjugate heat transfer problem, the momentum transport and turbulence, this is something that if you're familiar with CFD, you should know a lot about. So compressible, incompressible Navier-Stokes. And with this particular setup that we have within HELYX, you can choose different turbulence models based on if you're running in steady state or transient. Within energy transport, there's energy transport within the fluids itself and within the solids. And the way that the GUI is set up, we leverage a total enthalpy formulation that takes care of mechanical power and thermal power. The multiple solid and fluid regions, they present a meshing challenge and also a modeling challenge. And one thing that you might note is, on the right, we've got different fluids that might have different properties. We've got different solids that will have different physiochemical properties. But then also there's different length scales. So you might have a solid that would be, several millimeters thick or centimeters thick, or an entire solid component, or you might have some sort of solid film or layers of films in between the fluid and the solid. Okay, so we've got different length scales and the different physiochemical properties between the two regions. There's different time scales of this thermal transport within the system. So there's lots of challenges that we can encounter. In terms of modeling, the traditional multi-region method is what we would call partitioned. So we're doing separate solves of each equation in each region. So there's a thermal equation. If there's 10 solids, then there's 10 different thermal equations that we're solving. The domains are explicitly coupled through boundary conditions. The boundary conditions lag the solution. So that would be Jacobi coupled. And this approach of the boundary conditions being explicitly coupled between each other. So we solve one, we have a boundary condition, and then we transfer that information to the next region and use that as input as we solve. And then we'll go through and solve each one of these over and over and over again until it's relatively converged for that particular time step. Doing this approach, it impairs the speed and stability of this system. Within HELYX, there's a new multi-region method, and it's called region coupled. The strength of this is that it's a solution of a single equation in a monolithic matrix solver. So we take all of the different solids, all of the energy equations, and we put them all together in one single matrix, and we solve that. At the boundaries, instead of explicitly coupling, we're implicitly coupling through the boundary interfaces. Implicitly coupling means that the contributions from each one of these different domains are included within this matrix, and we solve them directly. Being fully implicit, it means that it's fast and robust. And one of the reasons, or one of the ways that how HELYX is set up, it employs the standard tried and true solver machinery. So we're using, if we're talking about from a programming perspective, we're using some of the classes that OpenFOAM is already has all the machinery that's already there. So we didn't have to reinvent a lot of things in order to make this work with things that are very trusted. So let's talk about the transport equations and really how the implicit coupling works. And this is a very broad view. So on the left, we've got the enthalpy transport equation for a fluid, and on the right, we've got an enthalpy transport solution or equation for solids. We discretize both of these, and during this discretization process, using the FV matrix class, we'll be able to assemble the AX equals B system. So if we think about it this way, we've got a matrix right here representing all the different weighting coefficients within the mesh, and this would be the matrix setup for the fluids, and then on the right we've got the matrix for the solids. Traditionally, using a partition approach, then we would take those matrices and then we would throw them into an LDU matrix, and then we would solve each one of those separately. However, in a monolithic matrix, we're still using LDU matrix. However, we're pulling them together into one single matrix, and these green dots right here represent coupling terms at the interfaces. So at the boundaries, we've got these other weighting coefficients that can account for the different contributions at the interface for connecting these two regions together. And the reason why we want to do that is because we want to have one region, the fluxes between one region affect the physics in the other region. And so this coupling term within the matrix allows it to be implicitly coupled. That way, when we solve the AX equals B system for this entire system, then it's much faster and more stable. So that's the meaning behind the implicit coupling. So let's talk about a verification case. So here we have the HELYX CHT solver, and the first verification case is a solids only case. We're just verifying the monolithic solution. It's 6 regions with various different thermal diffusivity ranges, and there's multiple internal heat sources. So here on the right, we've got the region coupled, and on the left, we've got the partitioned. And you can see that the region coupled converges extremely fast compared to the partition. In fact, the region coupled converges within 1 iteration, whereas on the left for the partitioned, it goes on to several hundred and greater than 1,000 iterations to converge this system of just solids. So, here I say the partition multi-region solver requires hundreds of iterations. So this is a very straightforward case. They're all linear equations. It should be solved very quickly. And the monolithic approach definitely solved it a lot faster. Okay, let's look at another case. This is one fluid region with 5 solids, and there's different heating regions. The results are identical versus the partitioned approach. And so the partitioned approach, if you're familiar with OpenFOAM, uses this CHT multi-region simple foam. Here on the right, again, we've got the region coupled, and these glyph vectors right here represent the fluid flow. On the left, right here, we've got the partitioned approach. And we see that the region coupled didn't converge after 1 iteration, because we've got a fluid solution also that we need to develop. It took a little while longer. However, there's significant speed up in convergence time. So this purple line right here is the partitioned, and this green teal line right here is the region coupled. And so we can see that it converged just a little bit around 20 seconds, and then we see that the partition took a little bit longer, and it's converged at almost twice the time. So let's talk about something a little bit more serious than just these verification cases. And one example right here would be a blade server. Within this blade server, there's forced convection cooling, there's internal flow, there's volumetric thermal heating in the CPUs and the chips and the memory modules. And for this particular comparison, we did a comparison between, or there was a comparison between HELYX, OpenFOAM, and another commercial code, ANSYS Fluent. So looking at ANSYS Fluent versus OpenFOAM, so we see Fluent converged in several hundred iterations, and then we see OpenFOAM 2.4. This is a little bit older test case, but it still used the partitioned approach. It still was converging after 1,500 iterations. We can see that chip number 4 is still climbing, and also chip number 2 still climbing, and chip number 3. So still not quite converged. So this red line represents, it still has a little bit more to converge. This white line right here shows where the Fluent results converge. If we compare this to the to HELYX, we can see that HELYX converged a little bit more than 600 iterations, so not quite the same convergence level and number of iterations, but still it's very much faster than standard OpenFOAM using the partitioned approach. So if we do a little bit of comparison between the probe temperatures, so Fluent versus HELYX, and we've got the Fluent results right here in this column, and we did 2 different tests. One was using an ideal gas for the density, and then the other one was a constant density, just to see what the effect of having a constant density would be. So for Fluent and HELYX, we can see that the different temperatures that were converged at the end of this simulation were actually very close. And we can see it's just a little bit better with the variable, the ideal gas density, rather than the constant density. Here we can do a little comparison side by side of the Fluent results versus the HELYX results. And we can see if we look at 59 degrees Celsius, here we've got around 59 degrees Celsius. So the peaks are about the same. We can see a little bit of a difference in the distribution. In terms of performance, Fluent ran for 52 minutes on 4 Intel Xeon processors. OpenFOAM ran for greater than 400 minutes on 3 Intel Core i7s, and HELYX ran for 72 minutes on 3 Intel Core i7s. So these two used the same processor. The performance was comparable to ANSYS Fluent, considering the 3 versus 4. So ANSYS was run on 4 cores, whereas OpenFOAM and HELYX were both run on 3 cores. We see at least a 5 times faster convergence with HELYX than we see with the partition approach within OpenFOAM. And we can also see that HELYX and Fluent provide similar results. And I'll make a comment about that after this next case right here. So the next case is a mobile phone. This is a little bit different. There's natural convection dominated cooling. There's internal, there's external flow. There's more interconnected solid components, and there's also volumetric thermal heating with these different components. And there was a comparison between HELYX, OpenFOAM, and ANSYS. Here, we're going to start with a little bit newer version of OpenFOAM, so OpenFOAM version 3, and we can see with Fluent, it's converging around 65 iterations, and we see that OpenFOAM version 3 for this case is converging at more than 20,000 iterations. So I'd say it's relatively converged, or it converged just a little bit after this point right here with the CPU. Now, if we compare this with Fluent and HELYX, we can see that the number of iterations between Fluent and HELYX are more on the same order of magnitude. We can see that HELYX converged around 150 iterations. And so that's pretty good compared to another commercial code. Let's look at the temperature results. So here is the temperature flow field of the ANSYS results versus HELYX. And we can see that the 92 versus 96, we can see similar buoyant flow, similar temperature profiles above this mobile phone. We can see also similar profiles of temperature within this domain and on the different components. Let's look at the velocity results. Again, we can see similar natural convection above this device with, a core, a peak velocity in the middle of this buoyant flow right here. And we can see the speed, the max is 0.357. Here we're at 0.358. So it's nearly identical between these two cases. So the results between Fluent and HELYX are generally similar. However, the discrepancies are most probably due to the differences in radiation model for both cases. So the differences in the temperature that we saw in the blade server case and also for the mobile phone, I would say that those are more closely related to the differences in radiation models between the two software. The performance measured, the convergence was a measure of how fast the probe temperatures converged. For Fluent, this took about 11 minutes on 4 Intel Xeon processors. For OpenFOAM, it took greater than 1,000 minutes. And for HELYX on 4 Intel Core i7s, it took about 10 minutes to converge. So I'd say that when we're looking at these two cases, HELYX provides a viable alternative to traditional proprietary CHT solvers. And within HELYX, we have an end-to-end CHT simulation framework, which I'll talk about. So what are the enabling features within the GUI? One of the most important is the meshing component. So multi-region mesh generation, there's two different ways that we can actually generate a multi-region mesh. If you've used HELYX before, or you saw my meshing webinar, the last webinar that I did, you would have seen that we can generate different cell zones by using a boundary surface based. So you actually have a closed STL surface that represents your different region. You can do that way. Or we can use an approach that's called, it's a multiple material point based. So if we have different STLs or different surfaces that are physically separated from each other because they're both closed surfaces or groups of them are closed, we can use a material point and place it in each one of these different domains and be able to split up these different domains in that manner. There's also region management tools for splitting, importing, merging these different domains. So we're able to actually move around the different cell zones and really kind of manage our multi-region case. And one of the most helpful things is that there's automatic interface boundary creation. So if we've got something that has, 20 different regions, and each one of those regions are in somehow contact with other regions, it can become very tedious to manage how these different boundary conditions are set and mapped between each one of these different domains. So the way that the GUI is set up is that there's automatic interface boundary creation. So automatically names things in a very intuitive way. You can kind of see this with chip to default, chip to heatsink, and then in the default, which is the fluid region, we've got default to chip and default to heatsink. So we've got kind of the inverse boundaries. So it's easier to connect these two different regions together and know where these two, and in fact, also, if you click on each one of these different boundary conditions, it'll light up within the software and show you exactly what you're looking at. So aside from meshing, there's multi-region setup tools. So there's a customizable material database. There's isotropic and anisotropic conductivity. There's radiation modeling. There's conformal and non-conformal boundary interface mapping. And also there's contact resistance modeling. So I talked about the different length scales within the system. You can use this contact resistance modeling to approximate a very thin layer within the system instead of having to resolve that with a mesh. And I'll talk about that when I do a demonstration. We also have fluid and solid source terms. So we've got porous media. We've got something called a generalized reference frame in both the fluid and solid. And so GRF is very similar to MRF. However, it's much more versatile in that we can apply it to different shapes, different objects. And here's an example of kind of a break cooling. This is a solid region. It's not rotating. However, we're able to transport the thermal energy around this device using a GRF. Also, we've got heat sources, and there's many more source terms that we can add to the momentum equation, to the thermal equation. So some of the other enabling features within the GUI are the post-processing capabilities. We've got function objects, and these function objects will enable us to monitor solution health. So the min, the max, the mean will take averages over the entire volumes, averages on surfaces. We'll be able to extract average data. We'll be able to generate derived in situ data. Derived data would be something like vorticity or a heat transfer coefficient, something like that. There's also post-processing capability within the View tab. We can do clips and slices and isosurfaces and talk about streamlines. And then we can do things like groups and scenes. So we can group these different post-processing objects together. We can create a scene in order to take different pictures and capture different perspectives. And so with that, let me talk a little bit more about each one of these features by doing a demonstration. And so for this case, I'm going to do a demo using a shell and tube heat exchanger. Let me start a new case. Let me start with shell and tube. And I'm only going to use 2 processors because I'm on a Windows laptop. So when we start the GUI, after we've already selected our client-server architecture, client-server architecture is a capability within HELYX that allows us to connect to different resources. Right now, I'm connected to this machine, which is local. However, I could connect to something like our cluster in the United Kingdom, or a cluster that we have in-house here in the US, or another workstation in my office. So I'd be able to use the resources on that remote computer in order to use something that might be a little bit more powerful. But for today, I'm just going to use these 2 cores on this machine. So the entire process of setting up a problem, we go through mesh, setup, solver, and then we can post-process. We're up here in the top left-hand corner with the different tabs. Let me start with the mesh tab, and I'm going to use the default algorithm, and the mesh algorithm is what controls the layer addition algorithm within our system. For the base mesh, I'm going to do 0.025 meters. This will generate a background mesh that has a uniform characteristic length of 0.025 meters. Let me import my geometry. And for this case, I've got everything already in STL format. We're able to import step, IGES, OBJ. You can see right down here at the bottom, STL, OBJ, IGES, and step. And let me import those. So this represents STLs. All these STLs represent all of the different regions within the system. So what I need to do is first off, I need to set the surface refinements for each one of these different components. For the baffles, so these baffles are around the tubes within the shell and tube heat exchanger. So we've got 2 different regions. One's a warm side and a cool side, and we want to exchange energy between these 2 different regions. And these baffles actually help mix the fluid that travels through this system before it flows out. So it'll flow in down here and flow through this and improve the overall heat transfer within the system. So for the baffles, let's select a 1, 2. And you can see right here that this is the characteristic length of each one of those cells. Next, let's look at the outer shell and the different plates. So the outer shell is the outer region, and then the plates are kind of the caps of these tubes within the shell and tube heat exchanger. Let me set those to 2, 3. And again, you can see the characteristic length of each one of these cells. I'm not going to add layers. I don't need to add anything for the different inlet conditions, inlet patches. If you're doing a more, a realistic case, or you're doing kind of a more detailed approach, you might want to add layers to the surfaces of the different pipes, the different tubes. That might be able to resolve the boundary layers that are flowing around the tubes. But for this case, I'm just going to resolve it just enough so I can get a good mesh out of this. All right, next. So if you were at my last webinar, then one of the methodologies that I talked about was that you can create other meshes by going to this zones tab, and then we can select the different cells that are encompassed with this STL and create a cell zone in this way. That's kind of the classical approach. We generate MRF this way, we generate porous media, cell zones this way. However, for this case, because it's a little bit more complex and we didn't want to have to extract the bounding region of the fluids like you might have to in other software, then we'll use a multiple material point approach. And the way that I do that is I go to mesh options. Actually, wait, first, let me click over here just so we can see the domain. Let's go to mesh options. And then in this first tab right here, I'll select use multiple material points and I'll click OK. And then let me go back to material point. And now you can see the interface changed just a little bit. I need to add another region. So the first one is, let's call this cold region. And then the next one, let's call this hot region. Cold region is going to be at 0, 0, 0. I know there's a tube that runs right down this domain. If I didn't know what those coordinates were, then I could change my perspective just a little bit. And you can see for this one right here, this one's actually right in the very middle in the center tube. But then you can see right here, I've got the hot region. This one is just above the tubes. I can pull that one up just a little bit more just so it's in the region above the tubes. Okay, great. That's all I need to do. So right now I'm ready to mesh, and this takes about, on my 2 cores, it takes about 140 seconds if I don't have so many programs running. But for this case, what I'm going to do is I'm going to load a case that is already meshed, and just before I split the case. So let me go to recent, and let's just open up that case just to save a little bit of time. Okay, so here, if I want to, I can press 5. Whoops, wait, let's try another perspective. There we go, that was a 4. And then turn on and off the parallel projections just so I can kind of get a side view. So right here, this missing solid right here, these were the plates, the cap plates at the end. I didn't want to model the heat transfer or the heat transport within that. This is where the different baffles are. Okay, great. As it is right now, it's still one single domain, and I've got different cell zones. So I've got this cell zone that represents the cold, and then I've got another cell zone that represents the hot component. So this is the in, and then it travels around through these baffles and travels out. Now what I need to do is I need to split this up and actually create the multiple regions. And the way that we do this is by using split mesh up here in the ribbon under the regions. And if I had more than one cell zone, right here, this is more straightforward. I've got 2 different cell zones, but if I had other ones, I can drag and drop, just kind of click on it and hold down with your mouse, and you can move around to these different regions. So say I had porous media or MRF that are inside of a fluid region, but I wanted them to be inside of cold region as well, I can do that. So you can manipulate and move around these different regions within your list in order to kind of manage exactly what's getting split. So right now I've got 2 regions, cold region and hot region, that'll be split. Let me click OK. All right, perfect. So it did a little bit of checks on the mesh to make sure that it was high quality as it split up. And so we can see that several things happened. We can see that a new boundary condition was created, cold region to hot region, and then another one, hot region to cold region. And now instead of having one single region, I've got 2 different regions, the cold region and the hot region. All right, so lots of regions going on. We've got 2 different meshes in the same case, and it automatically created the patches that map in between. It's already split up the different patches that belong to each one of these different regions. For now, we're okay. We can move on to the setup tab. Now, the GUI is smart enough to know that if there's a multi-region mesh inside of here, that we want to do a conjugate heat transfer, we want to do a multi-region case. So a lot of the solution state is already selected. So within the setup tab, we start at solution and we move our way down this tree to all these different entries. So if we start at solution, it'll be segregated in that it's a segregated solve of the momentum equation. So it still solves UX, UI, UZ, and pressure separately for each one of these domains, but it's coupled for the enthalpy within the domain. We can do a steady or a transient. For this case, let's just do steady. And then all I need to do is make sure that my gravity vector is pointing in the right direction. For this case, let's just do in the -z direction. In terms of materials, we're only going to do one material, and we're not going to model the heat transfer or the heat transport within the solid itself. So we didn't resolve any one of these different plates, any one of these different baffles. We didn't resolve the thin tubes themselves, and I'll tell you, and I'll show you exactly how we handle that. So I can get rid of steel, and then we're going to use water instead of air. So let me change that material to water. All right, so that automatically changed all of our different physiochemical parameters. Let's go to modeling. So modeling in the cold region, it's going to be water, and we're going to use a RANS K omega SST approach. And for the hot region, we're going to use a RANS K omega SST approach. I'm not going to use radiation because the temperatures really aren't that high in this case, so I don't need radiation. Let's move on to the boundary conditions. So let's talk first about the tubes themselves. So it's a mapped wall. We're using a conformal sample mode, and it's automatically set the sample patch. So the kind of the twin of itself in the other region. So here we're looking at cold region to hot region, and the sample patch is from the other region, hot region to cold region. All right, so it's automatically set this up for us. So if you have, 20 or 30 different patches, then you're not doing twice the amount of work. All right, great. So this is a no slip wall, so we can leave the momentum boundary condition exactly how it is. And let's go to thermal. And because we didn't resolve the tube itself, and right now it's just this infinitely thin, there's no mesh that represents the thickness of that tube, but we want to make sure that we model the resistance of, or the effect of the tube actually having thickness. So here we've got 2 millimeters, and we're going to set a thermal conductivity of 50 watts per meter Kelvin. All right, we could, if we wanted to, we could do multiple layers. You can add multiple layers to this, and it does a 1D model between the system. But for this case, I'm just going to choose a 2 millimeter thick surface. So let's just click OK. And I don't need to do this for the other region. We only need to do this once, okay? All right, great. So in cold, oops, let me go back, make sure that I put that in there correctly. I think I hit cancel instead of that. Okay, great. So next we need to do the inlet conditions for the cold side. So in cold, that is over here on this side right here. Let's change the patch type to inlet, and we still want it to be a velocity boundary condition, but let's do a velocity with respect to the normal of the boundary itself. And this velocity is 0.05 meters per second. For thermal, we're going to leave the default of 300 Kelvin, and for turbulence, we're going to leave the default turbulent intensity and turbulent length scales. For the out cold, because this is the outlet, we can change that patch type to outlet, make sure that it's a fixed pressure, and we've got a fixed pressure of 1/6 pascals. For the outer shell, it's adiabatic, no slip, so we don't need, there's no heat transfer that's coming, that's leaving the system through that. If we wanted to, we could change this and do something like a convective heat transfer, meaning that there's air that we don't want to model itself, but there's air or some fluid outside of this that's convecting off of this patch. We can change it to a convective heat transfer. If we want to set it to a fixed temperature or a fixed heat flux, we can definitely do that. Or we can also do a time varying heat flux. If we chose this, we could also do a time varying heat flux or a total heat load. Okay, so we've got a variety of different boundary conditions we can use. Plate 1 and plate 2, these are the end caps right here. Again, there's no heat transfer between those. We're assuming those are adiabatic. We could also resolve those as solids themselves and model the heat transfer, but for this case, we don't need to worry about it. And then tubes, these are actually just the boundaries of the tubes themselves within the different baffles. We don't need to worry about them. We'll call those adiabatic. For the hot region, for the different baffles, we'll leave those as adiabatic. We've already taken care of the conformal mapping and the contact resistance for the patches in between. For the outer shell, we don't need to worry about that. Again, it's also adiabatic. And let's look for the inlet condition of the hot side. So let's change that to an inlet. And let's go to momentum, and let's change that to normal to the patch itself. And this is also going to be around 0.2 meters per second. And because this is the hot side, let's raise the temperature a little bit. So we've got 343. The out hot, we need to change that to an outlet. And again, we'll leave the default pressure of 1/86 pascals. And for thermal, even though it says fixed value temperature, it means that if there's any inflow at the outlet, so if there's swirl of the flow coming, as the flow is leaving, what would be that inflow temperature? And for here, we can either leave 300 or we can do 343. It's probably closer. It's going to lose some of the heat. So we can leave it at 343 if we wanted to. Plate 1, plate 2, we don't need to do anything. Cell zones, we don't need to do anything because we're not doing any cell zone models. However, if we had something else, we could do porous media. If we had other cell zones that were in the system, if we had like a filter or a baffle or something like that. For thermal, we could do different heat sources, semi-implicit heat sources or fixed temperature. So there's different source terms that we can add for each one of these different regions. Numerical schemes, here we can control the gradient, advection, and Laplacian terms within each one of our equations. I'm going to leave those as default. Solver settings, this is where we set our residuals for our inner iterations and also our relaxation factors. For this case, I can set a relaxation factor for for enthalpy as 1. I can do the same for the hot region. And by changing this to 1 for enthalpy, it's a linear equation. And what happens by raising the relaxation factor in this way, it actually speeds up the convergence. Runtime controls, for this case, let's just do 100 iterations. It's very coarse mesh. Write data, if we wanted to write data to Insight, we could add that. Field manipulation, if we wanted to do something like in situ data processing, so let's just do a field process just to kind of show you what that's about. Here we have a long list of things that we can output: Y plus, heat fluxes, vorticity, total pressure, strain rate, skin friction factor, shear stress on the wall, cell Reynolds number, things like that. So there's lots of convective wall heat transfer coefficient. So we can add lots of different components. We can do general operations on different variables within the system to find the gradients of pressure or the gradients of density, something like that. Let me just close that. We don't really need that. Monitoring functions. Monitoring functions are very helpful because not only can we extract important information, but it's also a sanity check that our simulation is giving us values within a reasonable range. So I like to use volume report just for that. Volume report will give us the min, the max, and the mean of whatever variable we put. So here, let's just do pressure, velocity, temperature, and our different turbulence parameters. If we wanted to only sense these variables within a specific cell zone, we can select that. Again, this is just for the cold region. Let's add another one for the hot region. And let's do the exact same. Temperature, velocity, K, omega, and buoyant pressure. Next, let's do a surface report in the cold region, and let's get the flux weighted average of temperature at the outlet. So out cold. All right, so let's do SR cold. So flux weighted average and homogeneity will give us kind of the standard deviation of this to give us an indicator of how uniform that temperature is, even though we've taken the average at the outlet. And this is our patch at the outlet. Let's do another one for surface report in the hot region. And let's choose fields. Let's do temperature. And then let's also look at the outlet of the hot region. Okay, so far we're good. Let's set up the field initialization. Let's use potential flow for the cold side And then let's use a Prandtl mixing length approach for the K and omega to initialize that. Let's do the same for the hot region. And then also Prandtl mixing length, and we'll leave that temperature is 300. And then all we need to do is hit initialize. Okay, we could, if we wanted to look, we could go to View tab and look at the initial fields themselves. Let me just go on to the solver and go ahead and kick off this simulation. So we've done our meshing, we've done our case setup. Let's go to solver, and then let me hit run solver. As it runs, it's going to populate the residuals for the velocities and pressures, and then also for the different enthalpies, or sorry, for the enthalpy equation itself. So you can see that evolve over time. Let's see how fast this takes. If this takes too long, I can load up a case. All right, we can see it's starting to move within our simulation. I can look at the surface reports. Let's look at temperature. Surface report gives us this dark red line, which represents the mean temperature, and then this band right here is the max temperature and the min temperature across that particular boundary condition, or that patch that we put the surface report on. Volumetric report, surface report, again, let's look at temperature. All right, we see a jump and it's starting to converge a little bit. We see these bands narrow, start to get a flatter mean temperature. Look at velocity. So overall, and we see K starting to converge. So volume report is a great tool to enable us to see exactly, to further evaluate convergence beyond something like just residuals. So we see the residuals dropping. If we wanted to, we could do moving averages on this information. So we could do the last 25 iterations of, let's pick something like pressure. So we can see pressure is converging over the last 25 iterations. After we've got more data, we can increase this number. So once this is finished, it's still going right now. Once this is finished, we can go to the View tab, and within the View tab, we can perform slices and clips of our data. We can insert streamlines. We can look at isosurfaces. One of the interesting things is to be able to do things like create groups and create scenes. And if we want to create a group, so I can hit create group, and let's call this the exchanger. So that's going to be my group. And once I click on one thing, it will light up in green of what things I can group together. So I've got all of my surface mesh within my cold region, and then I'm going to have all of my surface mesh within the hot region. And let's group all that together. Let's hit OK. And right here, I can change the opacity to 0.1 if I wanted to. So if I remove this right here, I could color this if I wanted to. All right, we're about 80 iterations in. So the reason why we'd want to do this is because if we had if we had streamlines within our system, we'd be able to see kind of the underlying geometry behind it. So just a few more iterations, and then I'll add some streamlines. All right, it's writing out the data, and then it should reload. All right, there we go. All right, so let's go back. Let's just look at our group again. Let me right click and do show only. And so that will just show our group that we've already got. Let me click on Streamlines. And to use each one of these different objects, first we have to tell it what kind of source. Each one of these different objects have different types of sources that we can use. For example, if we want to use a slice, we can use the geometries, we can use the different surface meshes, we can use the volume meshes. So we would actually operate on the STL surfaces. Same thing for the clips. If we want to use isosurfaces, then it only uses the volume mesh. If we want to use streamlines, then it only uses the volume mesh sources. So here, let's do streamlines within the hot region, and I'll leave the name default as streamlines. I'll let it go ahead and decompose the polyhedra. For this case, it doesn't really matter too much. If I want, I have several different options of setting how to release these Lagrangian particles that are going to be floating through this volumetric domain. So I can either do a point cloud source or I can do a patch source. And for a patch source, I can select, let's say, in hot. Let's see if I can change that temperature. Actually, before I do that, let me go all the way to the very end. Okay, there we go. And then let me make sure I've got this showing just so we have a little bit more perspective of, there we go. So we've got a little bit of information about how the flow of the hot fluid flows through the system. We can color by temperature. I can color by any one of the different variables. Let me just change that from T to say UMAG. So we'll have a little bit of information about what the local velocities are. And we can increase the number of points. So we can do, let's say 300. I can change the radii of these streamlines themselves. If I want to increase kind of, let's do 100, see if that affects it a little bit. There's some limits of exactly how many streamlines they can fit within this different patch right here. And so we have different controls of what the vector field for the different streamlines right now is just U, but if we had other simulations that had different U fields, we'd be able to select what vector fields influence the streamlines themselves. We can also change the opacity of these different streamlines. Now, let's just say that we have this and we're going to be doing several different simulations. What we can do is we can do something called a scene, and let's call this streamline scene. And what a scene will do is it will be a way for us to store the different directions of a camera if we wanted to make sure that we're taking pictures at the exact same angle at every single time. So we can control what the background colors are. We can disable having this logo in the background. We can control what groups are inside of this. And once we're happy with what our scene looks like, we can hit Save Scene. That way, if we move the geometry a little bit and we want to go back to where we are, we can go back and hit Apply Scene, and it'll snap it back to the original focal point and orientation. So this is very helpful if we're doing things like taking a lot of different images. Here, I just took a screenshot of that particular orientation inside of post-processing, so we can see that image showed up right there. Perfect. Now, all of this that I've been doing, we could script all of this, and we do all of this scripting through the Python macro language that HELYX has been programmed with. We're able to record each one of these different actions. We would do this using what we call journaling. I could have started from the very beginning and said start journaling, and then I would stop journaling. This is actually the topic of the next webinar, which happens in late February. And with that, we can run through a case by journaling, and then we could theoretically drive a design of experiments or do some other operations to automate a lot of these different processes. So today, I just wanted to hit on the major components and kind of present an alternative to how we would mesh with zones by using multiple material points. This exact test case, if you're already a customer and have HELYX and you'd like this test case, you can write us an email and I'll be happy to send this over to you in order to reproduce these results. So some take-home messages. The capabilities of HELYX rival other commercial codes, and HELYX is used in industry and does replace other commercial codes. So there's definitely companies that have used or are using HELYX right now and changed completely over from other commercial codes. This is an end-to-end conjugate heat transfer workflow. There's meshing, there's solving, there's setup, there's post-processing. And this whole technology is currently built on a multiphysics framework that is extendable beyond conjugate heat transfer. So that's kind of a look towards the future. Right now, this multiphysics is just conjugate heat transfer, but we could do other things like conjugate mass transfer and chemical reactions and combined heat transfer and mass transfer to do even more complex systems. So that's kind of looking forward for a multiphysics platform. In terms of events, there's an upcoming event, the 15th Open Foam Workshop here in the United States from June 22nd to 25th. ENGYS is currently the official sponsor of Open Foam, of the Open Foam Workshop. So make sure that you sign up for that. Also, there's an upcoming webinar, which I already mentioned. It's called Automating CFD Analysis Tasks with Python and HELYX. We'll discuss how to use Python with HELYX and discuss how to set up cases and manipulate Python macro to perform even more actions. That's on February 22nd. Also, you can visit blog.engys.com. You can subscribe for updates. You can get R&D notes. There's past webinars. There's information about continuous adjoint. And then also there's lots of HELYX and elements related content.